4 study methods, 1 stats exam, and a scholarship on the line. Alice swears by flashcards, Bob crams, Yvonne highlights everything, and Zed does every practice test he can find. They're all convinced their method works best and are confident enough to bet their grades on it. So how do we actually begin to figure out who's right? In this video, I'll show you a hypothetical example of how ANOVA uses the F ratio to determine whether at least one of these 4 study methods actually causes average grades to change. Imagine you found 20 students, 5 using each of the 4 study methods, and all taking the same course. Knowing this is the perfect opportunity to test your friend's study methods, we can track how each group performed over the semester on their exams and record their average grades. Since this problem involves looking at the average of multiple samples, we can use a one-way ANOVA to compare the averages of each study group to determine if there is any statistical difference between them, by reducing the chance of any being randomly better or worse. This is done by analyzing the variance within each group and between each group. The variance helps determine how different these groups are from each other, and if any are significantly different. To start, we need a clear experimental design, including a proper hypothesis. We start with the null hypothesis, which in our case is that all study methods your friends had were effectively the same and would each result in the same average grade at the end of the semester. So even if you use flashcards, cramming would theoretically give you the same average grade. The alternative hypothesis in our case would be that at least one of the groups would result in a changed average grade. Notice how I didn't say improved, as there is always the possibility that one would result in a worse grade, and ANOVA doesn't distinguish between better or worse, just different. It is important to note that there is also a condition that the data must be normally distributed. It is hard with a small sample size of 5 students, but let's assume our example is just for simplicity. We will also assume each student's grades are independent of each other and the students didn't cheat or interact with each other. If they had, it would have skewed the results and ruined the experiment from biased data. Finally, each group variances should be similar. If Alice's group had a huge variance, it doesn't necessarily mean hers is best, but could just have a few large outliers skewing the results. Levine's test would be useful for this, but given the variances are roughly similar, we can continue on without it. After gathering the data, we have the average grades of each group. These were flashcards being 75.8, cramming being 75.2, highlighting with 77.8, and practice tests with 79.6. With the overall grand mean being 77.1. From first glance, practice tests look like the winner, but is it a real win, or did the group just happen to get the students with the higher average grades by luck? Remember, we are just looking at samples right now. In order to make an inference about the population and to prove it's not luck, we need to run a one-way ANOVA, since we have 3 or more independent groups and 1 independent variable. Now that we've set the stage with our hypothesis and data, we can finally get into it. First, we need to look at the differences between groups. This is done by looking at the study group itself without considering individual differences. We find this by taking each group, we'll subtract it from the grand mean and square it. We'll then multiply this by the sample size and add them all together to find the between group sum of squares. For us, this value is going to be 60.2. Unfortunately, this by itself doesn't tell you much though, as we need to divide by the term known as the between group degrees of freedom, or your number of study groups minus 1. Therefore, our between group mean square value is simply just 60.2 divided by 3, or 20.07. This simply tells us the average squared variation between each group. However, this value isn't enough unfortunately, and we need to factor in individual differences within each group. This is because each student or member of the sample has an individual difference. Some may not have slept properly, didn't study enough, or even forgot to submit an assignment. This is commonly referred to as noise or error. The value we calculated before is usually also referred to as signal, with the F ratio being the signal to noise ratio. For the noise or within group differences, we can begin by finding how far each student is from their group's mean. Looking at Alice's flashcard group, we can see some students are slightly higher, but others did slightly worse than what the average tells us. This is also why variances should be similar, as this is where the bias can get introduced. Similar to before, we want to find the within group sum of squares. This helps penalize larger errors and find the average. We can then square each value and add it together to find the average squared difference within each group. In our case, this will be 47.6. However, like last time, this number doesn't tell us too much without dividing by the degrees of freedom. For within group degrees of freedom, it is slightly different but the same idea, where we can just take the total number of students, which is 20 in our case, and subtract the number of groups we have, so that being 16. So the within group mean square is again a ratio of 47.6 divided by 16, or 2.975, which is just the average squared difference of each person within their group. Now, for the moment we've been waiting for, finding the F ratio. The signal to noise ratio, or dividing by the average group's difference by the average individual difference, will help us determine if any group's means are statistically different. If the F value is close to 1, then the study methods don't matter too much and any difference is due to random chance, so you can choose the easiest study method for you. However, for a large F ratio, then that indicates the signal is loud and strongly suggests there is a difference in at least one study method's average grade. After calculating the ratio, we find the F ratio to be 6.74, which strongly suggests at least one of our group's means is different and implies you can reject the null hypothesis claim that all study methods are equal. While this test is great, how much over 1 do you need to be? To be more rigorous and confidently reject the null hypothesis, we can also use a statistical distribution for the F statistic we calculated from the F ratio. This distribution is the F distribution, and we can use an F distribution table with our degrees of freedom and compare it to our F ratio to see this. In simple terms, what we are looking for is that the number found from the F ratio test is bigger than the F distribution table's value, as any value greater would have to be rare to have happened by random chance. We will use an alpha value of 0.05, which gives us a 95% confidence. If our result is greater than that, it would have to have been a 5% chance that we would have gotten as extreme or more of a result by random, assuming the null hypothesis is true. Using the F distribution table for an alpha value of 0.05 with 3 degrees of freedom for the numerator and 16 for the denominator, we find our critical value of 3.24. Comparing it with the F ratio from before, it is clear that 6.74 is greater than 3.24, and so we can confidently reject the null hypothesis. So in the end, it turns out your friend's study methods were not all equal, and the study method does indeed matter. So next time they start saying that their methods will improve average grades and get them that scholarship, you can have confidence that at least one of their study methods will change their grades. Just maybe not for the better, as ANOVA only proved a difference, not improvement. But it is also important to clarify, we are now making an inference about the population of study methods. Before, we were only using sample statistics like the sample mean of a few flashcard users, but now we can infer information about the population. Now, while we can celebrate at finding a statistically significant difference, ANOVA only tells us that at least one group is different. To find out specifically if flashcards beat cramming, you would need to run a post-hoc test, something like a Tukey's honestly significant difference test, but that's a story for another video. Subscribe not to miss it, and leave a like and comment.